Okay, so welcome to topic 22, resistance. So we're almost there in electricity. We've got resistance, circuits, and semiconductors kind of left to do. Effects of electrical circuits. That's the last two chapters after this are very, very theory heavy. Excuse me, especially semiconductors. Topic 23, let me see now. There are a few math questions, but it's a lot of theory too. I think actually pretty much all theory. There's about 5-6 questions in it. So this is kind of the last of the very maths heavy topics. Now this is part 1. This will be broken into 2 parts just because the notes are 14 pages long and I really don't want the video to be kind of 45 minutes. I find that people tend to find those difficult to follow. So what I'll do is I'm going to do up to page 6. Okay, I'll get down to resistivity. We'll halt it there and we'll continue on then in part 2. Okay, so don't need to talk about conductors. We've kind of talked about that before, but here we are. Resistance. What is resistance? The resistance of a conductor is the ratio of the potential difference across it to the current flowing through it, or R equals V over I. Okay, if you're asked to define resistance, you can give the math equation here because it means the same thing. But remember, if you give the equation, you have to give the notation. Okay, you can't just give one without the other. Okay. All right, the SI unit for resistance is the ohm, okay, which is this thing here. All right, so it's the ohm, all right, and that's kind of basically it. If you were asked to define the ohm, that would basically be look at your equation here. You'd have volts over amps. There you go. VA minus 1 equals ohm. Okay, that's the idea. All right, no, they never will, but it's nice to know it just in case. Yeah, okay. You measure using an ohm meter. You measure ohms using an ohm meter. You measure volts using a voltmeter. You measure currents using amps using a ammeter. Okay, do not say multimeter. Only say multimeter if you are really, really stuck, because chances are they won't give you the marks for it. Okay, Ohm's law. Here we go. So there is an equation or an experiment that you need to do with this as well. But what is Ohm's law? It states that the current flowing through certain conductors is directly proportional to the potential difference across it, assuming constant temperature. Now remember, you have to put in this bit at the end. Okay? That has to go in. Okay? Now you can, all right, you can, in the exam, go and write out current proportional to voltage, or potential difference. Make sure you say potential difference. Actually, don't say voltage. PD. But then you have to say assuming constant temperature. Okay? So you can give, as many people have asked before, can you give the math equation I is proportional to V? This. Can you give this? Yes, but you have to say this, and then you have to say this. Okay? Assuming constant temperature. If the temperature changes, you increase the resistance of the wires and you change the experiment. So you have to state that. That is worth 3 marks out of 6 that you get for that definition. Okay? And that's where the constant comes in, you see. All right? Because V is proportional. So I is proportional. Oh my God, is that meant to be a proportionality? Proportional to V. You have to make it a constant. Okay? So it has to become a constant. All right, so therefore V is equal to or I. All right, the reason it's or, okay, is because the constant is of course the temperature, which of course affects the resistance of the wire. So that's why the constant is there. That's why it's important to note the constant. Okay, they're all in the log tables. Don't worry about them. Variable resistors. I'm assuming you've seen them in the lab. It's basically a rheostat. You basically, as you move the sliding contact, you increase the number of wires that the electricity has to go through, and therefore by increasing the number of wires the electricity has to go through, you increase the resistance. And that's kind of how dimmer switches work, okay, as you can see here. All right, now we're getting up to the derivations. Resistors in series. So the diagram here shows resistors in series, and similar to voltages, you add them up. Okay, so R1 plus R2 plus R3 equals R total. Okay, so resistors in series, you add up, then you get the total resistance. Okay, so the question you're going to be asked is prove this. Show that resistors in series add up, and what you say is, well, voltages in series add up. V equals V1 plus V2, V equals IR. Okay, V equals IR, that's in the log tables. All right, so therefore IR total is equal to IR1 plus IR2 plus IR3, divided across by the i's, because all the i's are the same. R1 plus R2 plus R3 equals R total. That's it. That's your derivation. Okay? Fairly straightforward. Now, funny enough, that one doesn't get asked as much as the next one, because the next one's slightly harder. So, resistance in parallel, we know that 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay? Where does that come from? All right? So, remember, in series, the voltages add up, okay, to the total voltage. In parallel, the currents add up to get the total voltage. And again, it's the same thing. You just say, well, I total is equal to I1 plus I2 plus R3. V equals IR. V's are all the same, so they divide across. Voltage in a parallel circuit is the same. And you're done. That's it. Those are your derivations. Okay, fairly straightforward, fairly easy. Okay, so problem 1. The current through a conductor is 4 amps. The potential difference across it, 20 volt. Calculate the resistance. V equals IR, R equals V over I. So my resistance here should work out to be 5 ohms. That was a horrendous 5 ohms. Problem 2. What current flows through a resistance? 100 ohms when it's connected to a 230 volt supply. V equals IR, so I equals V over R. 2.3 amps. There you go. Very straightforward. These are very easy, guys. All right. So, a certain temperature, the current through a conductor is 3 amps. When the potential difference is 24 volts, find the resistance. Okay? When the temperature of the conductor is raised, the same PD, but a different current. Okay, so I'm going to take it in 2 parts. I'm going to break that up. All right? So, of course, V equals IR, R equals V over I, R equals, I got my resistance there is 8 ohms. For part 2 then, voltage stays at 24 volts, but my current drops to 2 amps. Same equation, 12 ohms. There you go. And that's it. Okay. Find the increase. Oh, sorry, I didn't finish it. Find the increase. 12 minus 8 equals 4 ohm increase. There you go. So there was a 4 ohm increase, and we're done. Okay. All right. Oh, excuse me. Coronavirus or something. I don't have the coronavirus, or maybe I do. Who knows? So the resistance of conductors. So I'm gonna just fire through this. Yeah, so I'm actually going to do it just a little bit more. I'm going to go down to this, and I'll stop. Actually, do you know what? I'm going to keep going. This video, actually, it's a short topic. I'm getting through it quick enough. I'm actually just going to do the whole topic. So there's only one part to this. Okay? So resistance of conductors. The resistance of a conductor depends on 4 different things: the length, cross-sectional area, the material, and the temperature. Okay? So these are the 4 things that will affect the temperature or the resistance of a wire. Its length, cross-sectional area, the material it's made from, and of course the temperature. Okay. Now you will be asked the resistivity. Okay. What is the resistivity? All right. It is defined as the resistance of a cube of material of side 1 meter. It's a lot easier than the resistance of a material of unit length L and cross-sectional area A. Okay. Now again, where that could come in handy is the equation is, rho equals RA over L. So resistivity, you could easily remember this one. Unit length L, cross-sectional area of A. So that might make it a little bit easier, okay? And the right? But you can't give the math. Could you give the math equation here? Actually, you could, but you'd have to give the notation as well, okay? So length. So basically, as you can see, resistance is proportional to length, because if we increase the length here, you increase the resistance. So the more wire there is, the more resistance there's going to be. So resistance is proportional to length. For cross-sectional area, it's inversely proportional, because if you increase the area of the wire, you decrease the resistance, because there's more space now for the electrons to travel through, okay? So, therefore, if a conductor of length L, cross-section area A, has a resistance of R, then there is a constant, the resistivity, given by that. Okay? The resistivity is basically the constant here of the wire. Okay? Now, first things first, I'm going to skip these two problems here, and I will come back to them, because I want to go to problem 7 first. All right, a uniform wire of length L, diameter D, and resistance rho has a circular cross-section area. Prove that its resistivity, rho, is given by R pi squared D, R pi D squared 4L. Okay, right. So what do we know? Rho equals RA over L. Okay? So we got to prove that this equals this. So we look at our area. What is our area? It's area of a circle, which equals pi r squared. Okay? What is radius? Radius is half diameter. So r equals diameter over 2. So therefore, area equals pi d over 2 squared. Okay? Which equals pi d squared over 4. So we sub that back in. Rho equals r pi d squared over 4 over L. What happens if you have a fraction above the line? You pull what's below the line as well. Rho equals r pi d squared 4L. And there you go. That's where it comes from. D being the diameter. Okay? Radius is half the diameter. So therefore, the radius is equal to diameter divided by 2. And that's where we get it. Rho equals r pi d squared 4L. Okay? You can use that in the exams to answer the questions, to jump straight forward. So if they give you the radius, instead of trying to find the area and then slot it back in, you can literally jump to this equation and do that. Okay? Sub in all your values. All right? It is allowed. Now, problem 4. A piece of wire of uniform cross-sectional area has a resistance of 28.2 ohms and a length of 0.892 meters and a diameter of 0.22 10 to the minus 3 meters. And we want rho. So we know that rho equals, where's my equation? Sorry, R A over L. So if you forgot about this equation, okay, R pi d squared over 4L, okay, let's say you forgot about that. You could, of course, you'd have to find that. So you go A equals pi r squared, find that, sub that back in here, same thing. So you'd end up with the same answer, it's just a bit longer. My way is a little bit shorter. I just use this equation, fired in all my values that I have. I have R, I have L, I have D, and I ended up with 1.2 by 10 to the minus 6 ohms per meter. Okay? Oops, I never said what that is. Rho. Oh, and why is it ohms per meter? Rho equals RA over L, right? That's ohms, A is meters squared, and distance is meters. So that cancels off that. That's where that comes from, okay? All right? So you have two ways to do it. You can find A, sub it in, or you can just go straight to that equation. All right. I always go straight to that equation, but you don't have to, all right? All right, problem 5. What is the length of wire? What length of wire, cross-sectional area of radius, so R equals 0.25 by 10 to the minus 3 meters, of resistivity is needed to make a resistance of 12 ohms. And we're looking for length. Okay, so again, the same thing. You would have to go and find A and sub it in, okay? Or you could literally go, so rho equals RA over L. So we're trying to find L. So we're trying to find L, which would be RA over rho, okay? So you can, yeah. So your options are, guys, you can literally find A pi r squared, solve it for there, which is fine, okay? So A pi r squared, and sub that back in up here, and you should get your length of 138.6 meters. Okay, that time it might be better just do that, okay? But you could also switch it up and do the diameter. So if they give you the radius, you can just swap out a for pi r squared. Okay, that's all. 6, 20 ohm resistor consists of a piece of wire of uniform cross-sectional area and of length. Don't forget, you have to convert all your units, guys. If the resistivity of the material of the wire, rho, calculate the diameter. So we're trying to find the diameter this time. Okay, so again, rho equals RA over L, or rho equals R pi d squared over 4L. We're trying to find D. So D would equal to, that'd be 4L times rho divided by resistance pi, and you get the square root. How did I get that? You basically bring up 4L, divide by R pi, and then you get the square root. Okay, that's where it comes from. Your diameter there should work out to be 3.28 by 10 to the minus 4 meters. And there you go. That's it. Donezo. Okay? So again, kind of fairly straightforward. Just remember what A is. It's the radius of a circle. Or it's not the radius of a circle, it's the area of a circle. Okay. Measuring a Wheatstone bridge. Okay, basically with Wheatstone bridge, you have you set it up so that the galvanometer reads 0. It's balanced, okay? Now the trick with this is R1 divided by R2 is equal to R3 divided by R4. You see? That's how you do it. So when you look at the Wheatstone bridge, you look for the plus side of the battery, see where that's going in, okay? And you'd have your R1, your R2 divided by R3, your R4, okay? That's how you always do it, because they could always twist it and have it on its side, okay? And all you do is a little bit of maths to find the missing resistor, okay? Now, the reason this works is it's usually used in fire alarms, whereby if the temperature increases, the resistance in one of these resistors will change. And what that does is, because that changed, the Wheatstone bridge is no longer balanced, which means the current flows, and that triggers the alarm, okay? So that's how it works, okay? Temperature controls and fail-safe devices, okay? Now, for a meter bridge, same kind of principle. The longer side of the battery is the plus, the smaller side is the minus. So it goes this way, okay? So it's this divided by this equals this divided by this, okay? Except instead of resistance on the second time, we have lengths. So length 1, length 2. That's how you do it. Whatever they are opposite, okay? Whatever you are opposite, all right? So find where the plus of the battery is, follow that around, okay? And that'll tell you what's on top and what's on bottom, okay? Plus side of the battery. And there you go, all right? And that's what happens here. R1 over R2 equals L1 over L2, all right? Except the difference here is you move the connector on the wire over and back until the galvanometer reads 0, and then it's balanced, all right? Now, kind of questions. Last time this came up was 2007. It hasn't come up since, so I think you should probably know about it, unless of course this video is after 2020 where they've brought it in. So this is a 2007 question. Now, so let's read the question. We have our Wheatstone bridge here, okay? We have values. We have a 20 ohm, we have a nichrome wire, we have that distance, that distance. This is the plus side of the battery, that's the minus, so that's coming over here. So that is R1, that is R2, that is L1, that is, oops, not L2, L1, that is L2. Oh my God, will you give me the rubber, please? Thank you. L2, okay? All right, that's how you figure it out. Where's, again, all right, so I'll do that again. So we look at the picture, determine what's the plus side of the battery. The longer side of the battery is the plus, that's the minus. So it's going this way and then back, okay? So therefore, that is R1, that is R2. This is L1, this is L2. That divided by that is equal to this divided by that. Okay, they're equal to each other. And there you go. That is how you solve it. All right, so that's how we set it up. So I'll write all my values out here now. Sorry. All right, R1, 20 ohms. R2, I'm just going to leave it as the unknown resistor. L1 is equal to 0.718 meters. L2 is equal to 0.282 meters. Right. So R1, R2, L1, L2. We're looking for R2, so R1 is equal to R2 times L1 over L2. So that will become R1 times L2 over L1 equals R2. Again, I do it this way. You can, if you wish, sub in your values. Once you get to here, you can sub in your values here to find this and sub it across. That's fine. All I'm doing is I multiplying across by L2, dividing across by L1, and that's why my fraction appears like that. I sub in all my values, which were 20, 0.282, 0.718. And let me see, what do I get? So 20 times 7.855 ohms. There you go. Done. Okay, so fairly straightforward. Okay, easy enough to do. Now the next thing I wouldn't worry too much about. If you're doing applied electricity option, then this kind of comes into play for you, but I generally don't, so I'm just going to ignore that. I don't do that. Now, the last thing I want to cover with you is the following steps. So basically, for all circuit questions, there is a pattern. If you follow this method, okay, you will be able to answer every single circuit question without fail. Okay, there are 3 steps. I'm going to talk you through the 3 steps, and then I'm going to give you the example. So step 1, establish, all right, you need to establish the total voltage supplied. That's easy enough. That's given to you in the battery. Next, find the total resistance of the circuit. Okay? So remember, how do you add rules? And by the way, page 616 of Real World Physics book. Okay? All right. And total current can then be found using I. So you need to find the total voltage, which is usually given to you. You need to find the total resistance. So you need to add up all the resistors. The resistors in series, you add up. The resistors in parallel, you have to do 1 over R. Right? Then you use that, I equals the total voltage divided by total resistance, to find the total current. Okay? It's the first step you do. Okay? Step 2, we need to find the isolated resistor. Okay? There will always be one resistor on its own. Start with that. Find the total current flowing through that resistor. Okay? To find V. All right? Oh, sorry, the total current flows through that resistor. Sorry. Because remember, in series, the current is the same, but the voltage is different. So we find the voltage going through that one resistor. Step 2, calculate all the remaining resistors. Subtract the voltage associated with the isolated resistor from the total. And now solve it. All right, so here's how we do it. All right. We have a diagram here. What's the question? Calculate the current flowing through in each resistor. So we've got to find the current going through 1, 2, 3 resistors. All right, we got to find it. All right, so how do we solve it? Well, step 1, we said the total voltage was 12 because it was given to us. So we calculate the combined 15 and 30 ohms. So basically, we looked at these resistors here. 1 over our total equals 1 over 15 plus 1 over 30. Okay? All right? So you have to find that first. That's what they did. All right? And they found it to be 10 ohms. Okay? Do not get trigger happy and say, well, if we invert all of them, we'll have R equals 15 plus 30. Okay? Don't do that. All right? 1 over 15 plus 1 over 30. All right? Then invert. That gives you an answer of 10 inverted. Now, your total resistance is 10, 10 plus 4. Why? Because it told us that the bulb had a resistance of 4 ohms. So 10, this was 10. This works out to also be 10, and that is 4. Okay? So our total resistance here is 24. So the total resistance in the circuit is 24. So the total current is total voltage, which we were told was 12. 12 divided by 24. Current is 0.5 amps. Okay? Look for the isolated resistors. We have 2 isolated resistors here. We have the 10 and we have the bulb. Okay? So for the 10, fairly straightforward. The current is 0.5 amps. The resistance is 10. The voltage is 5 volts. For the bulb, the resistance is 4. 2 volts are taken up. So therefore, of the 12 volts in the current, only 5 volts are left. Because if you remember, V1, V2, V3, and all 3 of them will equal the total 12. Okay, the voltage through the first thing plus the voltage through the second thing plus the voltage through the third thing equals the total voltage. So therefore, there's 12 volts. One takes up 5. The other takes up, what do we say, 2. So we're left with 5 volts. All right. So 5 volts, therefore, is going to travel through this circuit. Okay. Only 5 volts is left. All right. So to find the current in each one, okay, you simply say VI equals V over R. And the voltage in a parallel circuit is the same. So it's 5 in the top, 5 in the bottom. It all is the same, okay? Which becomes then these, okay? Now, there is another way to do it. You can do it this way, but I find it very awkward and complicated. Now, sounds very confusing. The trick with it, guys, is go back, follow those steps, okay, and practice a few practice questions. And whatever, regardless of what physics book you're using, have a look at the circuit section and try answer a few circuits one after the other, and you realize what is happening. You can follow this video along for it, okay? That is resistance done there, guys. That is all of it. Again, you can leave any questions you have in the comment section below or on the Edmodo page, and I'll get back to them as soon as I can.